So heat is a form of energy. It's thermal energy. Historically, there have been two main units for energy. One comes from physics. It's a joule. That's the energy needed to apply 1 Newton of force over a distance of 1 meter. And 1 joule comes out to be equal to 1 kilogram meter squared per second squared. So you can directly relate it to the SI base units. So a joule is the SI unit for energy. In chemistry, we've used calories for energy a lot because that is the energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So a lot of times in chemistry, you're heating up solutions of chemicals. You need to know how much heat will increase the temperature of your water, whereas in physics, you're maybe using energy to move masses over distances. The relationship between these two units is now defined. So this is defined or exact. So when we do these conversions, we don't need to worry that we are being limited to 4 significant digits. Another type of energy that you come across is nutritional energy. It's a little confusing because they also use the word calorie, but to tell the difference, we capitalize the C, and we capitalize it because a nutritional calorie is equal to 1,000 of the calories that were just defined above, or 1 kilocalorie, kilo being 1,000, 10 to the 3 calories. Also, these units are all very small as it relates to the energy you're using in your house with your electricity. And so another unit of energy that you can have is a kilowatt hour, which is quite large, 3.6 million joules. So we should be able to use these relationships to do conversions. This one is something that was talked about, mentioned in your LibreText. So the chemical energy that something has, a certain chemical, like for example, gasoline, has energy stored in it. The gasoline is capable of providing energy when you set it on fire and do chemical reaction on it that way. And so this is a form of potential energy. This potential energy can be converted into thermal energy if you burn some gasoline, or into kinetic energy if you cause an explosion and make something fly up in the sky. So this is potential energy. And then this is something that we talked about just here in the note packets, in addition to being in LibreText. These are all units of energy. The Newton is a unit of force. And to become energy, you have to apply this force over a distance. So force times distance would be energy, but the Newton itself is just force. Okay, so let's try doing this conversion. Remember that every relationship that you have can be expressed as 2 different conversion factors. Let's go ahead and do the kilowatt hour first. Between these 2 conversion factors, this is the one that is more useful because we'll cancel joules by putting that on the bottom. Let's go ahead and cancel the joules. So this time I thought I would practice putting a problem like this into the calculator, even though it has scientific notation. And the way you would type this into the calculator is to type 6850 divided by, and then 3.6 EE6. So your EE or EXP button on your calculator is the times 10 to the button. So this would be EE or EXP button on your calculator. And my calculator gives me 1.9 times 10 to the negative 3 kilowatt hours, or 0.0019 kilowatt hours. Let's go ahead and convert it to calories. Again, we want to cancel joules, so we'll use this conversion factor with joules on the bottom. And here our beginning measurement has 3 significant digits. The conversion factor is exact, so we will round it to 3 significant digits. So that is 1,640 calories. Now for the last conversion, let's do it over here. Converting it to nutritional calories, we'll use this one. So it's only 1.64 nutritional calories. Since we are talking about heat and energy, I wanted to introduce the terms endothermic and exothermic. We're going to be talking about this a little bit more when we talk about reactions as well. But if something is endothermic, it means you have to put energy into it. It's a process that's absorbing energy. And if it's exothermic, like the word exit, it means that energy is coming out. So this is a process that releases energy. And then we've mentioned the difference between temperature and heat, which we can see in the units used. There's different units that are used. Another important thing to remember about this is that a temperature is an intensive property. So you can have a large container of something and a small container of something both having the same temperature, but the amount of heat contained would be different because a very large beaker of hot water has more heat energy that is able to transfer than a small beaker of hot water. We've already talked about some temperature unit conversions in a different lecture. So let's move on to the relationship between heat and temperature. They are related because when you add heat to something, the temperature will increase. When you remove heat from something, the temperature will decrease. And it depends on the substance that you are heating. Some substances are very easy to heat. You can transfer just a little bit of heat to raise the temperature, whereas some substances are much more difficult. You need a lot more energy to raise the temperature of that substance by the same amount. Also, the amount of substance that you have plays a role in how much heat you need. So the specific heat tells how much heat is needed to raise the temperature of 1 gram of that specific substance. We'll equalize everything to 1 gram by 1 degree Celsius. We've mentioned that the heat that you need depends on the specific substance, which is the specific heat a lot of times expressed by the variable C. If you want to use SH to remind yourself that this is specific heat, that's okay too. It also depends on the mass, and it depends on how much you want to raise the temperature. If you want to raise it a lot of degrees, you're going to need more heat. Only a few degrees, you're only going to need a little bit of heat. And it's directly related to all three of these quantities. So the heat is equal to the mass times the specific heat times the change in temperature that you're trying to achieve. So this is a very important equation. We'll start off by solving for heat, but you should be able to solve for any of these variables, rearrange the equation, and solve for the specific heat, for example, or even the mass or the temperature change. So any one of these variables should be accessible. In this equation here, the Q is the heat that it takes to raise the temperature of something, depending on the mass, the specific heat of the substance, and the temperature change. So this is heat. And remember that heat has the units of joules or calories. Let's go ahead and rearrange this equation to solve for the specific heat, C. So if we divide both sides of this equation by m and by delta t, then on this side the m cancels and the delta t cancels. On the right side of equation we just get C, and then on the left side we have the heat over the mass times the delta t. So this is how you would calculate the heat capacity of something, the specific heat capacity of something. And we have another copy of this formula down here. So the specific heat is the heat over the mass over the delta T. So if the heat is in joules, and the mass is in grams, and the change in temperature is in degrees Celsius, the specific heat would have the units of joules per gram per degree Celsius. Or if the heat had been in calories, the units for specific heat would be calories per gram per degree Celsius. So remember that the heat is different from the specific heat. The heat is the energy measured in joules or calories. The specific heat is a property of a substance which would have these units here. Before we try some calculations with this formula, let's take a look and make sure we're understanding the concepts. So here we're looking for a property that does not depend on the amount, which is also called an intensive property. So an intensive property does not depend on the amount of material present. Extensive property does depend on the amount. So something that would be the same for a 1 gram piece of copper and a 1 kilogram piece of copper. So they could both be the same temperature. If you had a very hot piece of copper, both pieces would be very hot, but they would not have the same amount of heat. If you have a piece of copper that is small, it is not going to have the same amount of thermal energy in it as a piece of copper that is larger. However, the specific heat, the amount of heat needed to raise the temperature of 1 gram of the copper 1 degree Celsius is the same for all copper samples, no matter what their size, because it's the heat required per gram. So that's going to be the same. All right, so this takes a little bit of familiarity with metal versus water, whether it's easier or more difficult to raise the temperature of metal than of water. And hopefully we know that metal is easier to heat up than water. If you had a piece of metal out in the sun, you might be more scared to touch it than if you had a glass of water out in the sun. So it's easier to heat up the metal. It takes less energy. The specific heat is the heat it takes to raise 1 gram 1 degree Celsius. So the specific heat of the metal, since it takes less heat, the specific heat is lower. We can see that from this equation. If the heat is going to be less, if the heat is lower, and the mass and the temperature change are the same, then the specific heat also has to be lower. Because if the specific heat were higher, it's multiplied, that would make the heat higher as well. For the rest of this lecture, I'll just go through the problems 3.5.3 to 3.5.7. So if you want to just try these on your own and look at the answer key, that's fine too. If you want to see them worked out, then keep listening. This problem we are solving for heat. We are told the specific heat, the mass, and the beginning and ending temperatures. So we have some temperatures, mass, and specific heat, and we need heat, which is Q. So we need this equation. The change in temperature is the final temperature minus the initial temperature. So 38.4 degrees Celsius minus 22.6 degrees Celsius. I'll just go ahead and do this up and down so we can check our significant digits. With a subtraction, we need to look at place value, and it goes 1 place past the decimal. 15.8 is the temperature change with 3 significant digits. So now we need to multiply these 3 quantities together. The grams are going to cancel, and the degrees Celsius are going to cancel, and we're going to be left with joules, which is a good unit to have for heat. This is a multiplication, so we need to pay attention to the number of significant digits in each number. Our answer is going to need 3 significant digits. Once I've rounded my calculator's answer to 3 significant digits, I get 33.8 joules. So for this next one, we have the specific heat of gold and we want the specific heat of gold. So we want the specific heat, but just using different units. So this problem is just a unit conversion. Here are our 2 possible conversion factors. We want to cancel the joules and start talking about calories. So we need this one on the left. This will cancel the joules and introduce calories. Nothing is happening to the grams and degrees Celsius, so they will stay in the answer. Our answer will be in calories per gram degrees Celsius. All right, starting with this specific heat that has 3 significant digits and converting it using a conversion factor with infinite significant digits, an exact conversion factor. My calculator gives me a lot of digits. I should round that to 3 significant digits. These leading zeros are not significant. Don't count those when you're counting. First, second, third. There's your 3 significant digits, and it should be 0.0306 calories per gram degree Celsius. Here is another problem where we need to find the heat by multiplying the mass times the specific heat times the change in temperature. When we calculate the change in temperature by subtracting the initial minus the final, we come out with a temperature change that only has 2 significant digits, even though the temperature readings each had 3, because they only go 1 past the decimal. So this only has 2 significant digits. When I multiply all these numbers together, my calculator gives me 64.2. The units for that, since the degrees Celsius and the grams cancel, the units should be calories. And the significant digits should go down to 2 significant digits because of the temperature. So the final answer here should be 64 calories. This problem here, we are trying to calculate the specific heat. So we want to calculate C. Earlier in the lecture, we rearranged that to find that C is the heat over the mass times the change in temperature. We are told the heat and we are told the mass. We still need to calculate the change in temperature. That change in temperature is 22.4 degrees Celsius. None of these units cancel each other, so we're going to have this in calories per gram degrees Celsius. As for the significant digits, we have 3 significant digits in the numerator, a value with 3 significant digits and one with 4 significant digits in the denominator. So we are going to need 3 significant digits in our answer, which makes it 0.216 calories per gram degrees Celsius. This problem here is asking what temperature the piece of iron will end up at. So this is the final temperature. We know the initial temperature, and we want to know the final temperature. We know that the temperature change is the final minus the initial. So if we add the initial temperature to both sides, we can see that the final temperature can be obtained by adding the change in temperature to the initial temperature. And that makes sense. If this is our initial temperature, 22.5, and we discover that there is a 10-degree temperature change, then it will end up at 32.5. So we need to find the temperature change. We know the initial temperature, but we don't know the temperature change yet. Let's save this spot over here. And let's rearrange this equation to isolate the change in temperature on this side. We can do that by dividing both sides of the equation by the mass and the specific heat. So the delta T would be the heat over the mass times the specific heat. The heat that we supplied is 782 joules. The mass was 43.06 grams. And the specific heat is 0.449 joules per gram degrees Celsius. So here's a little math trick that you can use. If something's in the denominator of the denominator, like this grams degrees Celsius is in the denominator of this number, and this number is in the denominator of our calculation here. Instead of drawing another slash here, you can use the slash that is already present. So instead of putting this here, I will put joules here, and then I'll put grams degrees Celsius on the other side of this line rather than drawing an additional line here. Maybe we'll take a moment to talk about why this is true. If you have a number and you are dividing it by a fraction, then that is the same as taking that number and multiplying it by the inverse of that fraction. So this 2 that was in the denominator, when you're dividing it by 1/2, you actually put that 2 in the numerator. So 6 divided by 1/2 is the same as 6 times 2. So something that's in the denominator of the denominator goes into the numerator, and it is 12. So if you have 6 cookies and you want to give each person half a cookie, you will be able to feed 12 people. The reason I wanted to show you that is because I don't want you to get discouraged and lose track of your units. So just remember that if there's joules per gram degree Celsius in the denominator, the gram degree Celsius can go into the numerator. And this is very helpful because now the grams cancel and the joules cancel, and we are going to end up with degrees Celsius, which is what we should have for a temperature change. We're calculating the temperature change. We expect that to be in degrees Celsius, no joules or grams all over the place there. I'm getting a little crowded here, so I will go ahead and round this to the correct significant digit while I'm calculating it instead of writing down all the digits for you. And the correct significant digits would be 3 significant digits because of both the heat and the specific heat. And this ends up being 40.4 degrees Celsius. So this is our temperature change. The piece of iron will increase in temperature by 40.4 degrees Celsius. However, it started at 22.5 degrees Celsius. So if it starts at 22.5 and it has a delta T, an increase of 40.4 degrees Celsius, then the final temperature will actually be 62.9 degrees Celsius. So this is the final temperature.